1 billion years from now, Voyager 1 will still be out there. And if you want to know where, there is a calculation that practically does itself. Take the farthest machine human beings have ever sent into the dark. Look up its speed. About 3.5 times the distance between the Earth and the Sun every single year. Multiply that by 1 billion years. The math hands you a number in the neighborhood of 55,000 light years, which is more than half the width of the entire Milky Way galaxy. So the answer sounds settled before the question even finishes. 1 billion years from now, Voyager 1 should be impossibly far away, out past the far side of the galaxy, maybe beyond the galaxy altogether. A lonely machine sailing through the black ocean between the islands of stars. That answer is wrong, and it is wrong in a way that changes the entire ending of this story. Because that easy calculation rests on one enormous, invisible mistake. It assumes the galaxy is standing still. The galaxy is doing no such thing. The sun is moving. Every star you have ever seen is moving. The floor underneath this whole journey is turning. And once you account for that, the math turns strange and wonderful. The true length of Voyager's journey comes out far longer than 55,000 light years. And yet the machine itself may end up closer to home than anyone expects. It can fly perfectly for 1 billion years and still finish the trip. In a way, nobody sees coming. A local. Here is what makes tonight the right night to ask. On November 18th, 2026, Voyager 1 will officially reach a distance of 1 full light day from Earth. And NASA has already worked out that moment down to the second. We know where this machine is right now with almost absurd precision. Yet nobody on this planet can tell you where it will be in 1 billion years. Tonight, we are going to find out why. We are going to run the calculation ourselves. You and me. And push it as far as physics will let anyone push it. Until we arrive at the last honest address anyone will ever write down for Voyager 1. So, get comfortable. Turn the lights down. And let us begin where every calculation has to begin. With the one position we still know for certain, somewhere in the high desert of California, about an hour north of Barstow, there is a valley full of giant white dishes. This is Goldstone, one of 3 stations in NASA's Deep Space Network. And if you could stand there tonight, under the same darkness you are lying in right now, you would see the largest antenna slowly tilting toward one particular patch of sky. It is listening. It has been listening. On and off, for almost 50 years. What it is listening for is almost nothing at all. Voyager 1 transmits with about 23 watts of power. That is roughly the strength of a refrigerator light bulb. By the time that signal crosses the gulf to Earth, it has spread and thinned and faded until the power arriving at the dish is a fraction of a billionth of a single watt. Engineers have spent decades hunting for comparisons that do the weakness justice. And the comparisons always sound made up. The battery in a wristwatch is billions of times more powerful than the whisper Goldstone pulls out of the sky. And still the dish catches it, night after night, buried under the static of the entire universe. There is a thin thread of order, a rhythm of ones and zeros, and it belongs to us. Follow that thread backward, and you arrive at the machine itself. Right now, as you listen to this, Voyager 1 is roughly 16 billion miles from Earth. Light, the fastest thing there is, needs almost a full day to cover that distance. So the conversation between Earth and Voyager has become the slowest exchange in human history. Suppose the team at the Jet Propulsion Laboratory in Pasadena sends a command on a Monday morning. Something routine. A request for a status report. That command races outward at the speed of light. and it spends all of Monday flying. It arrives on Tuesday. Voyager obeys, answers, and the reply spends all of Tuesday and most of Wednesday coming home. Ask a question on Monday, hear back on Wednesday. 2 full days. For one round of small talk between a planet and its own machine. And the gap is still growing. Voyager 1 is pulling away from the Sun at about 38,000 miles per hour. A little more than 3.5 times the distance between the Earth and the Sun every year. It has held that pace for decades without burning a drop of fuel. Because nothing out there slows it down. Just momentum. Patient and paid in full. Carrying it outward through the dark. Which brings us to a date worth circling. November 18th, 2026. In the small hours of that morning, at a moment NASA has already calculated down to the second. Voyager 1 will reach a distance of exactly 1 light day from Earth, 16.1 billion miles, 173 times the distance from the Earth to the Sun. From then on, every message we send will take more than 24 hours to arrive. And every answer will take more than 24 hours to return. No machine we have ever built has been that far away. No machine has ever been close. Now, look at what that announcement quietly reveals. Because it is the most important clue in this entire story. NASA did not say Voyager would cross the light day line sometime in November. They did not say sometime that week. They named the day and the moment months in advance. For an object 16 billion miles out, in the dark, beyond the last planet. They can predict its position so precisely that they can schedule a milestone the way you would schedule a dentist appointment. Think about how that is even possible. There is no camera anywhere that can see Voyager. No telescope on Earth or in orbit can photograph it. It is far too small and far too dark. A 1-ton machine the size of a small car. Its main antenna about 12 feet across. Lost in an ocean of black. Everything we know about its position comes from that whisper of radio. From the timing of the signal. From tiny shifts in its frequency. From the geometry of 3 antennas on a turning planet. Engineers can pin down the location of this invisible speck to within a few miles. 16 billion miles away. And we know where it sits to within a few miles. That is more than an estimate. That is an address. There are people whose whole working lives are wrapped around that address. At the Jet Propulsion Laboratory, there is a small team, much smaller than in the glory days, that still tends this mission. Some of them were not born when the spacecraft launched. They pull up the numbers. They check the health of a machine older than they are. And the numbers always answer. Distance, velocity, direction, a row of figures on a screen, updated continuously, telling us exactly where our farthest traveler is at this exact moment. Hold on to that screen, because it is the real main character of tonight. A quiet room in Pasadena, a row of numbers, an address 16 billion miles long. Tonight is the story of how that address dies. Because here is the strange truth sitting under this whole mission. All that precision, that beautiful certainty, is a candle. It stays lit only as long as the machine keeps talking. And the machine is running out of the ability to talk. Distance was never the problem. Voyager could coast for 1,000,000 years and the physics would not blink. What it is running out of is something far more ordinary. Something you deal with every day of your life. It is running out of power. And when the power goes, something remarkable will happen to that number on the screen in Pasadena. It will keep updating. It will look exactly the same. But it will quietly stop being knowledge and start being faith. Right now, tonight, the address of Voyager 1 is a fact. measured and confirmed 16 billion miles at a time. Enjoy that certainty while you can. It is the last certainty this story will ever offer. Every machine you have ever owned died in a way you could point to. The screen cracked. The engine seized. The battery swelled up one summer and refused a final charge. Voyager 1 is going to die differently. It is going to die the way a house at the end of the street goes dark. One window at a time. So gradually that nobody in the neighborhood could tell you afterward which night it actually happened. The heart of the spacecraft is a set of 3 generators mounted on a boom, held out away from the body. There are no solar panels anywhere on Voyager. And there is a good reason. Where it flies. The sun is just a very bright star, thousands of times too faint to power anything. Instead, each generator holds a core of plutonium, and that plutonium does the only thing plutonium ever does. It decays. Atom by atom, it falls apart. And every falling atom gives off a small pulse of heat. And the generators turn that heat into electricity. No moving parts. No fuel pump. No off switch. Just radioactive warmth bleeding steadily into power. Exactly as it has since the summer of 1977. But decay is a one-way street. Every year there is a little less plutonium left. A little less heat. And so, a little less power. The decline is astonishingly gentle. About 4 watts per year. 4 watts. A nightlight. That is all the mission loses annually. When Voyager launched, its generators produced roughly 470 watts. Today, after nearly half a century of that slow leak, the budget is down to less than half of what it was. And the team in Pasadena has been forced to become the most careful accountants in the solar system. Their ledger works like this. Every instrument, every heater, every gyroscope on board draws its share of watts. And each year, the shrinking budget has to cover the bills. When it cannot, something gets turned off. Forever. Over the decades, the cameras went dark. Heaters were sacrificed. And experiments that had finished their work were retired one by one. In 2025, the team shut down the cosmic ray experiment that helped prove Voyager had reached interstellar space. In 2026, another instrument followed it into silence. As I tell you this, the spacecraft is running on a skeleton crew of sensors. A couple of experiments, still tasting the space around it. Still radioing home what the wind between the stars feels like. The engineers believe they can nurse it along a few years more. Past the 50th anniversary in 2027, if they are clever and lucky, perhaps into the early 2030s. And then comes a day with nothing left to turn off, except the voice itself. Nobody can tell you the exact date. It may end with a planned farewell session. Or it may end when the power dips below what the transmitter needs and a scheduled contact simply passes in silence. A dish in California, listening to an empty channel. What we can say is how quiet it will be. There is no crash at the end of this story. No fireball. No debris. No wreckage sliding across a desert. The spacecraft will be in perfect motion the whole time, holding its speed, holding its course, missing nothing but its voice. One day it is the farthest thing we have ever talked to. The next day, it is just the farthest thing. Here is the part I find genuinely hard to sit with. The people and the machine are on the same clock. The men and women who built Voyager, who calculated its path and folded its antennas for launch, are now deep into their 70s and 80s and 90s. And some of the greatest of them are already gone. The mission's legendary project scientist, who guided it for half a century, passed away in 2024. The team replacing that generation is young. and devoted. And every one of them knows the same thing. Sooner or later, someone at a console in Pasadena is going to transmit a command, an ordinary string of instructions, and it will happen to be the last one. They may not even know it at the time. Somewhere in the next decade, a human being will speak to Voyager 1 for the final time in the history of the world. And the odds are good that nobody will realize it was goodbye until the silence has lasted a while. You might expect the story to end there. A dead probe, drifting, but look closely at what actually changes on that day. Because it is less than you think. And that is the whole point. Voyager does not stop. It does not even slow down. Its speed came from gravity. From the giant planets it visited on the way out. Jupiter grabbed it in 1979 and slung it onward like a stone from a sling. And Saturn did it again in 1980, bending its path up and out of the flat plane where the planets live. It has not fired an engine to change course since. All the momentum it will ever need, it already has. And momentum does not run on electricity. The transmitter dies. The journey does not. What dies is our end of the thread. Go back to the screen in Pasadena, the one with the numbers on it. On the day after Voyager falls silent, that screen will look completely unchanged. Distance, climbing, velocity, steady, coordinates, ticking along. The software will go right on calculating where the spacecraft ought to be. And for years, for centuries even, those numbers will be excellent. Because the road out there is smooth and the math is good. But something invisible will have shifted in what those numbers actually are. Today, when the screen says Voyager is at a certain spot, we check. Because the spacecraft answers, and its answer confirms the math. After the silence, there is no answer. There is only the math. Projecting forward, alone, unverified, forever. Today, the position of Voyager 1 is a measurement. The day the radio dies, it becomes a prediction. And the rest of tonight is the story of what the galaxy slowly does to a prediction before we can send Voyager into the deep future. We need to settle a question that sounds simple and turns out to be anything but. Has Voyager 1 actually left the solar system? You have probably heard that it has. It was headline news around the world in 2013. And if you search for Voyager tonight, article after article will hand you the same sentence. Voyager 1. The first human-made object to leave the solar system. I remember how good that sentence felt. It is also, depending on what you mean by leaving, not quite true. And the gap between those two meanings is about to swallow 30,000 years of this story. So let us get it right. Here is what genuinely happened. The sun does more than shine. It blows. From its surface pours a constant hurricane of charged particles called the solar wind, streaming outward in every direction at 1,000,000 miles per hour. And that wind inflates a kind of bubble around the sun and all its planets. Inside the bubble, the space between the worlds is filled with the sun's own breath, its particles, its magnetic field, its weather. Astronomers call the bubble the heliosphere. And it is enormous. It swallows the orbits of every planet, all of them with room to spare. But the bubble has a wall. Push far enough out and the solar wind runs out of strength. Because it is pressing against something, the space between the stars has its own thin fog of particles and its own magnetic field, the mingled exhaust of other suns. And where the outbound wind of our star finally stalls against that interstellar fog, there is a boundary. On one side, the sun's weather. On the other side, the weather of the galaxy. In August of 2012, Voyager 1 hit that wall and went through it. The spacecraft could feel the change directly. Its instruments watched the count of solar particles fall off a cliff, while the count of galactic particles jumped. And the readings settled into a new normal that has held ever since. The bubble was behind it. For the first time in history, a machine built by human hands was tasting the raw material between the stars. And it took about a year of careful argument before the scientists were confident enough to say so out loud. Which is why the announcement came in 2013. This is the honest meaning of the headline. Voyager 1 left the Sun's atmosphere. It entered interstellar space. Every word of that is true. Now for the part the headline skipped. Leaving the Sun's atmosphere is one thing. Leaving the Sun's property is another thing entirely. And the Sun's property extends much farther than its breadth. Because the thing that actually defines the solar system is gravity. And gravity does not stop at the bubble wall. The Sun's pull reaches outward far beyond the heliosphere, weakening with distance, thinning, but never quite letting go, and drifting in that outer darkness. We are almost certain is the last and largest structure the Sun owns. A vast shell of comets, trillions of them, chunks of ancient ice left over from the construction of the planets. Circling the Sun in slow silence, so far away that no telescope has ever photographed the shell itself. We know it is there because every so often one of those comets falls inward and swings past us. And when astronomers trace the paths of those visitors backward, the paths all point out into the same immense region. Astronomers call it the Oort cloud, after the astronomer who deduced it. It begins hundreds of times farther out than Voyager is tonight. And by some estimates, it does not fade out completely until you are a noticeable fraction of the way to the next star. Hold that picture for a second, because it resets the scale of everything. The heliosphere, that bubble it took Voyager 35 years to escape, is a soap bubble sitting in the middle of a cathedral. The cathedral is the Oort cloud, and the Sun holds all of it. So, let us put Voyager on the map honestly. Tonight, it is about one light day from home, moving at about 3.5 times the Earth-Sun distance per year. At that pace, NASA's own estimate says the spacecraft will need roughly 300 more years just to reach the inner edge of the Oort cloud. 300 years. Everything it has done so far. Jupiter, Saturn, the crossing of the bubble wall. All of it happened in the Sun's front yard. And once Voyager enters the cloud, it faces the true crossing. Tens of thousands of years of flight through that thin haze of sleeping comets. The best estimate is that somewhere around 30,000 years from now, Voyager 1 will finally drift past the outermost members of the Sun's family and coast. At last. Off the Sun's property and into the open galaxy. If the word cloud worries you, it should not. The Oort cloud is emptier than any emptiness you can picture. Trillions of comets sounds crowded until you spread them through a volume that dwarfs the entire planetary system. And then the arithmetic turns comforting. The typical gap between one comet and its nearest neighbor out there is measured in tens of millions of miles. Voyager will cross the whole cloud, all 30,000 years of it. And the overwhelming likelihood is that it never passes close enough to a single comet to see one. If it had eyes to see, the danger out there is not collision. There is nothing to collide with. The only thing waiting in the Oort cloud is time. Now come back to that screen in Pasadena, because this is where our story quietly begins to turn. Tonight, the screen shows a dot. One precise point. Verified every day by a living radio signal. Sometime in the 2030s. As we saw, the signal ends. So picture the map 300 years from now. At the inner edge of the cloud, the software still plots a dot. And the dot is still probably excellent, because the spacecraft has been coasting through smooth, empty territory with nothing to disturb it. Probably excellent. There is the new word, sitting right where certainty used to live. Nobody has heard from the machine in almost 3 centuries. The dot is no longer a fact being confirmed. It is a forecast being trusted. And at 30,000 years, out at the far edge of the cloud, the dot has stretched into something more honest. A short, bright line. A small stretch of possible positions. Still narrow. Still confident. But no longer pretending to be a single point. That is the shape of things to come. The map does not fail all at once. It softens. And it has one more comfort to offer before the real darkness. For its entire crossing of the Oort cloud, Voyager remains, in the deepest sense, on home ground, inside the gravitational household of its own star. Voyager left the sun's weather back in 2012. It will spend the next 30,000 years leaving the sun's property. And the moment it finally steps off the property, something will be waiting for it out there in the dark. Or rather, something will be coming to meet it. Ask anyone who loves this mission where Voyager 1 is headed, and there is a decent chance they will give you the same answer. It is on its way to a star called Gliese 445. You will find that claim all over the internet, and it carries a lovely image with it. A little ship on a long voyage. A distant lighthouse, marking the destination. An arrival scheduled roughly 40,000 years from now. Some part of us badly wants that to be true. A journey ought to be going somewhere. What is actually going to happen is stranger than the lighthouse story. And in its own quiet way. Better. Gliese 445 is a red dwarf. A small, cool, dim star in the northern sky, sitting tonight about 17 light-years away in the constellation Camelopardalis, up near the celestial pole. You cannot see it. Nobody can. It shines with less than 1% of the sun's light. Far too faint for human eyes, even though it is one of our nearer stellar neighbors. It has no confirmed planets. Nothing about it stands out. Out of the 100 billion stars in this galaxy, it is about as ordinary as a star can be. And yet it is about to earn a permanent place in the story of human civilization. Because of a coincidence of geometry. Here is the first thing the lighthouse story gets wrong. Voyager was never aimed at it. Voyager was never aimed at any star. The direction it flies tonight, up and out of the plane of the planets toward the constellation Ophiuchus, was chosen by Saturn. By the geometry of that final flyby in 1980, the whole outbound path is simply what was left over after the spacecraft finished its real assignment. The planets and gravity flung it onward. Whatever lies along that direction lies there by accident. And here is the second thing, the one that turns the story inside out. In this encounter, Voyager is barely the one doing the traveling. The star is coming to us. This is one of the great hidden facts about the sky. The stars are not fixed. Every star in the galaxy is plunging along its own path at enormous speed. And Gliese 445 happens to be heading almost straight at the solar system, closing the gap at better than 100,000 miles per hour. That is nearly 3 times faster than Voyager flies. So run the next 40,000 years and watch what each traveler contributes. Voyager, crawling outward at its steady pace, covers a little over 2 light-years, a heroic distance for a machine, and barely a step on the map of the neighborhood. Gliese 445. In the same stretch of time, sweeps inward across roughly 16 light-years of space, crossing almost the entire gap between us, swinging past the solar neighborhood on its own long orbit around the galaxy. Put the two motions side by side, and the roles are impossible to miss. The little ship barely leaves the harbor. The lighthouse comes down the coast, passes by, and keeps on going. Astronomers can time the crossing, roughly 40,000 years from now. The paths line up, and Voyager 1 and Gliese 445 will make their closest approach to each other. Now for the number that matters. The distance between them at that closest moment. It will be about 1.6 light-years. Let me put that in units. This journey understands 1.6 light-years is roughly 600 times the distance between Voyager and Earth tonight. It is more than a third of the way from the Sun to the nearest star. If some observer stood on a world circling Gliese 445 at closest approach and looked out toward the passing visitor, they would see nothing whatsoever. A dead, dark, 1-ton machine, 6 trillion miles below their sky. No telescope humanity has ever built could find it at that range. The star will never know. So, why does every serious article about Voyager still mention this encounter? Why does NASA itself describe the spacecraft drifting within about 1.6 light-years of Gliese 445 in 40,000 years? Because out here, that counts as close. That is the lesson hiding inside this whole chapter. And it may be the single most important piece of scale I hand you tonight. The galaxy is so empty that a miss of 1.6 light-years, a miss 600 times wider than everything Voyager has flown in 50 years, qualifies as the closest thing to a meeting this machine will experience for tens of thousands of years. Interstellar space is not an ocean dotted with islands. It is an ocean almost entirely made of gaps. And the word near, out there, has to be stretched until it covers trillions of miles, or it covers nothing at all. There is one more clock ticking inside this encounter, and it is worth winding now, because we will need it later. 40,000 years is longer than it sounds. 40,000 years ago, there were at least 2 kinds of human beings walking this planet. And the other kind, the Neanderthals, were living out their final generations. Every alphabet, every wheel, every city, every nation that has ever existed fits inside that span with room to spare. Now run the same distance forward. By the time Voyager glides past Gliese 445, 1,600 generations of history will separate the people of that era. If people remain, from the summer morning in 1977, when this machine left Florida, whoever looks up at the sky that night will see no encounter at all. The spacecraft will be silent, invisible, and unimaginably far beyond anyone's reach. Its position, a forecast, run forward across 40 millennia. And yet, even then, the forecast still mostly holds. The flyby is loose enough. 1.6 light-years is far enough that the star's gravity will barely tug the spacecraft's path. The line on the map bends by only a whisper. Remember that whisper. Tonight, it is nothing. Given enough time, whispers like that one are going to take over this entire story. For now, hold the image as we leave the chapter. 2 travelers cross paths in the dark. A small cold machine and a small cold star, each one following its own orbit, neither one aware of the other, missing by 6 trillion miles. That is what a meeting looks like in this galaxy. The first star Voyager ever meets will never know it was there. So the first 40,000 years are accounted for. A slow climb out of the sun's property. A silent pass by a star that never notices. The natural next question is how far the map goes after that. If we can chart 40,000 years, can we chart 400,000? 4 million? Can we just keep running the film forward until we hit the 1 billion year mark that brought us here tonight? Somebody has actually tried. And the story of how far they got is the story of where human knowledge, real, checkable, honest knowledge, runs out. The tool that made the attempt possible is a European spacecraft called Gaia. And if Voyager is the great traveler of our era, Gaia is the great map maker. For more than a decade, it sat 1 million miles from Earth and did one thing with almost fanatical patience. It measured stars, their positions, their brightness, their colors, and above all, their motions. The slow drift of each star across the sky and the speed of each star toward us or away from us. By the time its survey was done, Gaia had charted nearly 2 billion stars. And, for the ones in our neighborhood, the measurements are so fine that astronomers can do something that sounds like science fiction. They can take the sky off pause. They can run the stars forward in time, or backward, and watch the whole neighborhood move. A few years ago, a small team of astronomers realized this new map made a beautiful question answerable. We know Voyager's path. Gaia knows the paths of the nearby stars. So run everything forward together. The dead spacecraft and the living stars, every object following its own track, and simply watch over the ages ahead. Which stars does Voyager 1 actually get close to? The answer came back, and it is wonderfully strange. Close passes are rare, a handful per million years. And the closest of them all arrives roughly 300,000 years from now, when Voyager drifts past a dim, unremarkable star known only by its catalog number, missing it by something like a light year. A light year. That pass. The closest thing to an encounter the study found in the ages it examined is still a miss, hundreds of times wider than everything Voyager has flown since launch. Everything Chapter 4 taught us about the word near gets confirmed again out here. The galaxy keeps its distance. For hundreds of thousands of years, nothing touches this machine. Nothing even comes close to coming close. But the truly important lesson in that study is hiding in a place most people would never look. It is hiding in the fine print, in the error bars, in the honest machinery of prediction itself. And that machinery is worth 1 minute of your night, because it decides everything from here on. Every measurement humans have ever made carries a tiny uncertainty. Gaia's star positions are miraculous, but they are not perfect. And neither are the measured speeds, and neither, for that matter, is our record of Voyager's own trajectory. Tiny uncertainties, all of them, now project a star's path forward. In 1 century, a tiny error in speed produces a tiny error in position. Fine. In 10,000 centuries, that same tiny error has been multiplying quietly the whole way. And the star's predicted position has smeared into a fuzzy region. Push further and the fuzz grows. And the fuzzy stars tug on the prediction for Voyager. And Voyager's own small uncertainties grow right alongside. Run any simulation far enough, and the answers stop being points at all. They become clouds of maybe. The astronomers who built that forecast knew this perfectly well, which is why they designed it for the near galactic future. The next several million years, where the star chart is still sharp enough to name names. They never claimed to be charting 1 billion years, and no one honestly could. A billion-year forecast would need to know things no catalog on Earth contains, where every star in the galaxy will drift across 40,000 times the span of human civilization, where the great clouds of gas will be, how the galaxy itself will shift its own weight, Gaia gave us the finest map of the stellar neighborhood ever drawn. And even that map, projected forward, dissolves into statistics long before the destination we are aiming for tonight. The film keeps playing. The picture goes soft, and no better telescope fixes it. Because the softness comes from the arithmetic of time itself. So let us go back to the screen in Pasadena and look at what has become of our beautiful number. Tonight, our dot, sharp and confirmed, at 40,000 years. Silence long since fallen. The dot has stretched into a short, bright line. A small family of possible positions. Still tight. Still proud. Now, push the display forward to 1,000,000 years and watch. The line widens. The single path becomes a bundle of paths. A corridor of possibilities sliding through the dark between the stars. Wider at the far end than the near end. Like headlight beams opening into fog. Voyager is in that corridor. That is a promise physics can still keep. Where in the corridor? No one can say. Now feel the size of the problem we came here to solve tonight. 1,000,000 years is roughly where the good map gives out. The question on the poster is 1 billion. 1,000 times past the edge of the finest star chart human beings have ever made. If you have been enjoying this journey so far, by the way, a quick like or a subscribe genuinely helps this channel keep making nights like this one. And now is a good moment for it. Because everything familiar ends here. Past this line there are no catalogs, no simulations, no forecasts with names in them. Past this line, the only way forward is the one scientists use when the map runs out. We stop asking exactly where the traveler goes, and we start asking what kind of place the road itself must carry it to. Which means it is finally time. Time to do the calculation everyone came here to do. The famous one. The big multiplication. The number that launched 1,000 headlines. It is time to find out what 55,000 light years really means. Let us do it together. Right now. Out loud. The most tempting calculation in all of spaceflight. You already have both numbers you need. Number 1. The speed. Voyager 1 covers about 3.5 times the distance between the Earth and the Sun every year. It has held that pace, steady as a metronome, for over 40 years. There is no air out there to drag on it. No friction. Nothing ahead with any business slowing it down. So we are allowed to assume the pace holds. Number 2. The time. 1 billion years. That is the assignment on the poster. Now multiply. 3.5 Earth-Sun distances per year. Times 1 billion years. Gives 3.5 billion Earth-Sun distances. Convert that into the currency of the galaxy. And the arithmetic hands you a number that deserves to be said slowly. 55,000 light years. Sit with that for a second, because it is a genuinely staggering result. The entire disk of the Milky Way, the great spiral city of stars we live inside, is about 100,000 light years across. Our Sun sits roughly 27,000 light years from the center, a little more than halfway out toward the rim. So, a budget of 55,000 light years reads like galactic money. Enough, on paper, to carry a traveler from our quiet suburb all the way in through the crowded core and out the far side. Aim it differently, and it reads like enough to cross the rim entirely. Leave the spiral behind, and sail into the true intergalactic dark. And so, you get the picture that half the internet carries around. The picture I carried around for years. 1 billion years from now. A tiny machine coasting utterly alone in the black gulf beyond the Milky Way. Our whole galaxy hanging behind it like a lit city seen from far offshore. Every star humanity ever named reduced to a smudge of light over its shoulder. The farthest thing, at the farthest distance, forever outbound. It is a magnificent image. Articles love it. Artists love painting it. And the multiplication behind it is, I want to be completely fair, correct. Check it on any calculator you like. The arithmetic is flawless. The answer is still wrong. And tonight, I can finally show you why. Because the mistake is hiding inside the most innocent-looking words in the whole calculation. 3.5 Earth-Sun distances per year. Ask yourself one question about that speed. The question nobody ever asks. Speed measured against what? Against the sun. That is what the number means. Every figure we have used all night. The 38,000 miles per hour. The 3.5 units per year. All of it describes how fast Voyager pulls away from the sun, which is exactly the number a mission team needs. Because their job is talking to the machine from here. But the moment you multiply that number by 1 billion years and call the result a journey across the galaxy, you have quietly done something enormous. You have treated the sun as a fixed landmark, a lamppost bolted to the floor of the universe, so that every mile gained on the sun becomes a mile gained on the map. Remember the hook at the start of tonight. The whole popular picture rests on the assumption that the galaxy is standing still. This is precisely where that assumption sneaks in. The sun is the ruler we measured with, and the ruler is moving. How much is it moving? Here is the honest scale of things. And it lands like a punch. The sun, carrying the Earth and everything you love, is sweeping through the Milky Way at roughly 500,000 miles per hour. Voyager's famous escape speed is 38,000. The lamppost is doing 13 times the speed of the machine escaping from it. So picture the real scene at last. A tiny probe, inching away from a star. While the star itself tears across the galaxy, dragging its whole family along. The probe included, because the probe inherited every bit of that galactic motion on launch day and never gave it back. Now watch what happens to the odometer. Measure Voyager's actual path through the galaxy. The true ribbon of road it lays down among the stars. And the 55,000 light-year figure collapses into a footnote, riding the sun's motion plus its own. The machine covers on the order of 700,000 light-years of real distance in 1 billion years. Read that again slowly. 700,000. 13 times the number in the headlines. The famous figure is not even the length of the journey. It is only how much the gap between two travelers would grow if one simple pattern held forever. And here is the twist inside the twist. The one this whole night turns on. That enormous true journey, 700,000 light-years of flying, does not carry Voyager 700,000 light-years away from anything, because the sun is making a journey of almost exactly the same kind, at almost exactly the same speed, through the very same galaxy, two travelers, racking up astronomical mileage, on paths that have every reason to stay tangled together. Which cracks the question of the poster wide open. If the small number is only a gap that assumes the galaxy holds still, and the big number is a road that goes who knows where, then what does the map at 1 billion years actually look like? Everything now depends on the shape of two roads, and the next 2 chapters are going to draw them. First, the strange geometry of roads in general, of odometers and addresses, and why they betray each other. And then the specific road the Milky Way forces every traveler onto. The sun and the machine alike. The picture at the end looks nothing like a lonely probe beyond the rim. 55,000 light-years was never the address at the end of the journey. It was never even the journey. Every May, in the flat middle of Indiana, 300,000 Americans gather around a 2.5-mile loop of asphalt to watch the fastest race in the country. The Indianapolis 500. The cars scream around that oval for 500 miles. Hour after hour. Engines at full fury. Drivers at the edge of what a human body can take. And here is my favorite fact about that race. The fact this whole chapter hangs on. After 500 miles of flat-out driving, the winning car ends up exactly where it started. At the finish line, which is the starting line. Distance from where it began the day? 0. Nobody at the speedway feels cheated by that. Everyone understands, without ever saying it out loud, that the odometer and the map keep track of two different things. The odometer on that winning car says 500 miles, and it is telling the truth. The map says the car went nowhere, and it is also telling the truth. Miles traveled and distance from your starting point only agree on one very special kind of road. A perfectly straight one. The moment the road curves, the two numbers begin to separate. And the moment the road bends into a loop, they divorce completely. You can drive forever on a loop. 100,000 miles. 1,000,000. And your distance from home will never grow beyond the far side of the track. Now bring that back to the numbers we just uncovered. Because last chapter left us holding two of them, and they cannot both be the answer. 700,000 light years. The true mileage Voyager racks up through the galaxy in 1 billion years. And 55,000. The number from the headlines, which turned out to be only how fast a gap widens between two moving travelers. Dressed up as a destination. Two numbers. One machine. The way out of the confusion is to admit that where questions come in 3 different sizes, and to take them one at a time. The first size is the odometer. Total road covered. Every mile counted. No questions asked about direction. For Voyager, across 1 billion years, that is the giant figure. 700,000 light years of genuine flying. Most of it inherited from the sun's own tremendous motion. The odometer is honest, and the odometer is huge. It is also, as every driver at Indianapolis knows, completely silent about location. The second size is what you might call the crowfly's number. Forget the winding path. Plant a flag at the exact point in space where the journey began. That spot in the galaxy where a rocket rose off Florida in 1977, and draw one straight line from the flag to wherever the traveler sits now. On the oval in Indiana, after the race, the crowfly's number is 0. On a straight desert highway, it equals the odometer. On any real, curving road, it lands somewhere in between. Always less. Never more. Every curve in the road is a discount on your escape. And the third size is the one the poster is actually asking about. And it is sneakier than the other two. How far is Voyager from home? Right now. At the same moment, look closely at what makes this one different. The first two measure against the starting point. A fixed flag. A dot of space that holds still by definition. But home is no flag. Home is the sun. And the sun is a vehicle. It was somewhere on launch day. It is somewhere else tonight. And it will be somewhere unimaginably else in 1 billion years. Asking how far Voyager is from home means measuring the gap between two moving things. And a gap like that has a life of its own. It can grow. It can shrink. It can grow for an age, and then shrink for an age. 2 race cars can each drive 500 miles and finish a single car length apart. And nobody who watched the race would call that a paradox. It is just what happens when 2 travelers share a track. 3 numbers. Then, the road covered, the line, back to the flag. The gap between two moving travelers on a straight road out of a parked hometown. All three collapse into one. Which is why nobody has to think about this, driving to Denver. And now you can name the exact sin of the calculation from Chapter 6. It took one number and wore it three ways. It assumed the mileage was the escape, and the escape was the gap, and the gap was the answer. Straight road. Parked hometown. Galaxy standing still. Every assumption false. And all of them false for the same single reason. So everything now rides on one question. The question the next chapter exists to answer. What is the actual shape of the road? Because if the road out there is anything like straight, the old picture survives. And the machine really does end up in the far dark with the galaxy behind it. But if the road curves, if the road does anything remotely like what that asphalt does in Indiana, then the odometer can spin past 700,000 light years, while the gap between the machine and its hometown stays. In galactic terms, small. To find the shape of the road, we stop watching the tiny machine. We turn around and watch the thing it is supposedly escaping. The biggest secret in the whole Voyager story was never on board the spacecraft. It is under your feet, and it has been moving your entire life. Somewhere over the middle of the country tonight, there is a red-eye flight. And somewhere on that flight, a passenger is tossing a bag of peanuts and catching it. Nothing about the toss looks strange. The bag goes straight up, hunks, and drops straight back into the same hand. And yet in the time that toss took, the airplane carried the passenger, the seat, the bag, and the hand about 500 feet through the night sky. The bag flew 500 feet sideways and landed in the same palm. Because the bag was a passenger too. It carried the plane's motion the whole way up and the whole way down. Nobody on board can feel that motion, and nothing on board escapes it. That little toss is the physics that owns the next billion years of this story. When you leave a moving vehicle, you take its motion with you. Jump forward off the back of a moving train, and you do not suddenly hang in the air while the train shoots away. You inherit the train's speed, all of it, and your jump merely adds your own push on top. To a farmer watching from a field, you are barely a person who left a train. You are a person flying across the countryside at train speed. Plus, a little. Now set the scene of September 1977 honestly. A rocket did not lift off from a parked planet in a still universe. It lifted off from a world that circles a star that is tearing through the Milky Way at roughly 500,000 miles per hour, bound on its long lap around the galaxy's center. A lap so vast, it takes about 230 million years to finish. The last time the sun was on this side of the track, dinosaurs were new. That is the train. And on launch day, Voyager inherited the ride. The entire 500,000 miles per hour came aboard with it. Free of charge. Exactly the way the peanuts carry the airplane. Everything we did afterward. The rockets. The flybys. The slingshots past Jupiter and Saturn. All the glory of the farthest machine we ever built. Amounts to the jump. 38,000 miles per hour of jump. Run the honest comparison, and it lands hard. The jump changed Voyager's motion through the galaxy by less than a tenth. Seen from the solar system, Voyager is a magnificent escapee, receding year after year. Unquestionably gone. Seen from the galaxy, Voyager is a passenger who changed seats. It is still doing roughly 500,000 miles per hour in roughly the same direction as the sun. Still riding the same carousel. Still circling the same distant center. The jump was real. The ride never stopped. Fair enough. You might say, but give it time. 1 billion years is a long runway. The machine escaped the sun's gravity. And that was supposed to be the hard part. Surely, eventually, it works its way free of the galaxy too. Here is where the sizes of things turn merciless. Because escape is always a question of speed. And only speed. To break free of the sun from where Voyager flew, it needed to outrun the sun's pull. And it does. Permanently. That verdict is in, and it will never be overturned. The sun cannot bring this machine home. But the galaxy is a different opponent, with a different price of admission. To leave the Milky Way outright. To climb away from the combined pull of hundreds of billions of stars and everything between them. An object in our neighborhood needs a total speed of very roughly 1.2 million miles per hour. Voyager, train, speed and jump combined, is traveling at less than half of that. It does not have the money. It is not close to having the money. And with the engines cold forever and nothing ahead but empty space, there is no way left to earn more. The deficit is permanent. What follows from a permanent deficit is one of the oldest rules in the sky. An object moving slower than escape speed does not leave. It orbits. The galaxy's gravity holds it, gently and forever, bending its straight line into a curve. And bending the curve around the center, the same iron law that keeps the moon circling the Earth and the Earth circling the sun. Applied one level up. So there it is. The shape of the road. The answer Chapter 7 demanded. The road is a lap. A vast, slow lap around the heart of the Milky Way. Tens of thousands of light years across. One circuit every couple 100 million years. Out there, a lap never traces the same painted line twice. The way a car does at Indianapolis. The galaxy's pull shifts. The path wanders. Each circuit lands a little differently than the last. But wander is all it does. Wander within the track. Bound is bound. And this machine is bound for good. And with that, the lonely image can finally be retired. The little light leaving the harbor forever. The machine alone in the black beyond the rim. The galaxy shrinking behind it like a lit city seen from far offshore. That picture was painted with the sun's motion left out. Put the motion back in, and the truth is stranger and somehow more intimate. 1 billion years from now, Voyager 1 is still in the Milky Way. Still on the carousel. Still circling the same center as the sun. The same center as every star you have ever seen. It jumped off the train with everything it had. And everything it had was enough to change its lane. And nothing more. Voyager escaped the sun. It never escaped the ground the sun is standing on. There is a moment in every long story where the main character stops being what they were and becomes what they are going to be. For Voyager 1, that moment has a date range. Sometime in the 2030s. When the transmitter falls silent, the word spacecraft quietly stops fitting. Think about what the word actually promises. A spacecraft has a mission. A spacecraft has a destination, or at least a direction somebody chose. A spacecraft is flown, steered, commanded, watched over. It belongs to somebody. Every one of those threads snaps on the day the power dies. After the silence, there is no mission, because a mission needs data coming home. There is no destination, because the direction was never chosen. It was whatever Saturn left behind. There is no steering, no commands, no team. What remains is a 1-ton object, dark and cold, coasting on a curved path through the Milky Way, obeying gravity and absolutely nothing else. And the funny thing is, the universe already has a word for objects like that. It has billions of them. We call them asteroids. No astronomer would file the paperwork. Asteroid is a category for natural bodies, and this object has a manufacturer. So, understand this as the narrator's nickname rather than an official classification, but watch how well the description fits. Because the fit is the whole point. Ask what an asteroid really is, underneath the movie image of tumbling rocks. And the honest answer is simple. A small body, far too small to be a planet, shining by no light of its own, traveling on a path determined entirely by gravity. Nobody flies an asteroid. Nobody needs to. Gravity does all the flying, and the asteroid simply endures for millions or billions of years, going around and around. Hold Voyager against that description after the silence. A small, dark body, no light of its own, no propulsion, a path bent around a center by gravity alone, maintained by nothing, interrupted by nothing. It matches every line. The only real differences are the aluminum and the nameplate. And this particular minor body belongs to an almost empty club. The asteroids you know all orbit the Sun. Voyager has resigned from that arrangement. Once it leaves the Sun's property, it will never again be bound to any star. Its lap is around the center of the Milky Way itself. The same carousel the Sun rides. The same carousel every star rides. Astronomers have recently begun catching small dark wanderers on journeys like that. Twice in the past decade, objects from other star systems have been spotted passing through ours. Little travelers owing allegiance to no sun. And each time, for a few thrilling weeks, people around the world asked the same half-whispered question. Could it be artificial? Could somebody have built it? Both times the answer was no. Just ice and rock on a long road. But savor the symmetry. Somewhere in the deep future, Voyager 1 is the yes. It is the genuine article the whole world was hoping those visitors would turn out to be. A built thing. On a galactic orbit. Drifting between the stars. So here is what I propose. And I will hold to it for the rest of tonight. From this point forward, I am going to stop calling this object a ship. A ship implies a harbor somewhere ahead. And there is no harbor in this story. What launched from Florida in 1977 was a spacecraft, brilliant and busy and loud with purpose. What coasts through the year 1 billion is something else. Something the solar system quietly manufactured and released into the galaxy the way an old tree releases a seed. A new, permanent resident of the Milky Way. 1 ton of 1970s engineering taking its place among the stars and clouds and drifting rocks. Subject to the same gravity. Keeping the same kind of time. Notice what the new identity buys it. Everything fragile about Voyager was tied to the spacecraft part. The power that had to flow, the instruments that had to work, the signal that had to be caught, the team that had to be funded. All of that was mortal. And all of it dies in the 2030s. The asteroid part needs none of it. Asteroids do not require maintenance. Asteroids do not need anyone to believe in them. The Milky Way is carrying rocks tonight that have been on their rounds for over 4 billion years, since before the Earth had a solid surface, and they have made every lap without a single watt of power. That is the club Voyager is joining, and the dues are zero. On the day it launched, we built a spacecraft, without ever meaning to. We also built the galaxy's smallest asteroid, and an asteroid, unlike a mission, does not end, which leaves exactly one thing standing between this object and the year 1 billion. The road itself. Nothing out there can stop it. But 1 billion years of interstellar road can still do something to it. Mile by mile, grain by grain. It is time to find out what. Start with the good news, because the good news is genuinely spectacular. The space this object is entering is the emptiest environment that exists. Interstellar space holds about 1 atom in every cubic centimeter. The air you are breathing right now packs billions of trillions of molecules into that same tiny volume. The finest vacuum chambers ever built in any laboratory on Earth are crowded, filthy rooms compared to the space between the stars. And that emptiness is a gift, because almost everything that destroys the things you own lives in the crowd. Rust needs oxygen. Rot needs water. Corrosion. Mildew. Decay. All of it runs on air and moisture and warmth. And out there, every one of those destroyers is absent. There is no weather between the stars. There is no morning dew. A footprint on the moon can last millions of years. And the moon is a busy downtown intersection compared to where this object is headed. So the vacuum is on its side. But the vacuum is not perfectly empty. And the two enemies that live in the almost are worth meeting up close. Come in close. Then, picture the great dish of the main antenna, 12 feet across, gliding through the dark somewhere past the Oort cloud. A few thousand years from now, out of the blackness ahead comes a grain of interstellar dust. A fleck of carbon and silicate thrown off by some star that died before the sun was born. It is smaller than the width of a human hair. It is also relative to the machine, moving at tens of thousands of miles per hour. And at that speed, there is no such thing as a soft landing. The grain does not bounce. It detonates. In a flash, too small and too brief for any eye, grain and a pinpoint of metal vaporize together. And when it is over, the dish carries a new crater the size of a pinprick. One crater, harmless. Now, let the clock run the way this story runs clocks. 1,000 years. A handful of craters. 1,000,000 years. And the polished face of the dish is going dull. The way beach glass goes soft and cloudy in the surf. One grain at a time. 100 million years. And the exposed surfaces are frosted over with microscopic scars. Edges gently rounded. Coatings worn thin. The sandblaster never rests and never hurries. It has all the time there is. That is the first enemy. The second one does not bother with the surface. The galaxy is crisscrossed by cosmic rays. Atomic nuclei accelerated to ferocious energies by exploding stars, and they rain on everything. Everywhere. From all directions. Forever. Down here, you are shielded by the Earth's magnetic field and by miles of atmosphere. The object has neither. The rays strike it directly, and the fastest of them punch through the aluminum skin as if it were fog, knocking atoms out of place as they pass, leaving little trails of disorder in whatever they cross. In the dead electronics, that hardly matters anymore. In the structure itself, it slowly adds up. Plastics grow brittle. Adhesives give out. Insulation blankets that once wrapped the body turn fragile as old newspaper and shred away under the dust. Metal endures far better, which is why the frame and the dish hold their shape. But even metal keeps the score at the atomic level. One tiny scar per ray. Forever. Now, for the honesty this channel runs on. Delivered once. So it covers everything ahead. Nobody can certify a machine across 1 billion years. No human material has ever been tested for 1,000th of that span. And the interstellar road itself varies. Thicker here. Thinner there. So the wear rate is an estimate. Never a promise. There is also luck. Some rare, violent encounter. A shattering impact with something large enough to matter. Can never be fully ruled out across a span that long. only judged deeply improbable in a galaxy this empty. So take this one sentence as the fine print for the rest of the night. Barring a rare, destructive stroke of cosmic bad luck, everything that follows is the expected story. And the expected story runs like this. The shape survives. The frame, the boom, the 12-foot dish, the unmistakable outline of a built thing. All of it still there in the year 1 billion. Frosted, pitted, dulled, and recognizable at a glance. Erosion is real, and erosion is losing. It works too slowly, against too much metal, in too empty a galaxy, to consume this object in the time we have on the clock. There is one part of the machine where that answer matters more than all the rest combined. A gold-plated case, bolted to the side, built by people who thought about this exact problem and aimed one component of Voyager at eternity on purpose. We will open that case later tonight. And the story of how it was armored against everything this chapter just described is one of the best parts of the whole night. For now, the inspection is done, and the verdict travels well. The road wears the traveler, and the traveler outlasts the road's patience. So hold the twin image as we close, because you have now seen this pattern twice. The position, blurring outward through the ages, from dot to line to corridor, and now the object itself, blurring the same way. From the crisp machine in the launch photographs to something softer, a range of possible conditions, brighter or duller, more worn or less. Depending on roads, nobody can chart. Time does the same thing to both questions. Where is it, and what is it? The answers stay real. They just stop being sharp. Space is not empty. It is just very, very patient. We need to talk about the clock. All night long we have been handling spans of time that no human calendar was built to hold. 40,000 years to pass a star. 30,000 to cross the Oort cloud. 1,000,000 to reach the edge of the reliable map. And somewhere past 10,000 years, if you are anything like me, the numbers all start landing in the same drawer. The one marked forever. Big. Bigger. Very big. All filed together. All feeling the same. If we are going to reach 1 billion years together tonight, we need a better clock than that. So, let me hand you the one the galaxy itself keeps. You already know the two natural clocks your life runs on, and you know where they come from. A day is one spin of the Earth. A year is one lap of the Earth around the Sun. Well, the Sun is on a lap too. We rode that discovery 2 chapters ago. The whole solar system circling the center of the Milky Way at 500,000 miles per hour. One enormous round trip. That round trip has a name. Astronomers call it a galactic year. And it lasts about 230 million ordinary years. One spin of the smallest hand. One lap of the largest one. That is the clock our asteroid now lives by. And on that clock, everything tonight has covered so far. The launch, the planets, the silence, the star that comes to visit, the entire million-year map. All of it fits inside the first tick. So let the clock run. Let one galactic year pass. 230 million ordinary years. And let us take stock of what a single lap of the Milky Way actually does. The machine itself simply rides. Frosted and patient. As we saw, what one lap does to everything else is the part nobody warns you about. Start with the sky. And brace yourself. Because the sky is the first casualty. Every constellation you have ever recognized will be gone. That is bookkeeping. Plain and simple. The stars of the Big Dipper look like a family. but they are strangers at different distances, each on its own orbit, each moving in its own direction at hundreds of thousands of miles per hour. On the scale of a human life, those motions are invisible, and the sky feels eternal. Give it 100,000 years, and the dipper's handle bends out of shape. Give it 1,000,000, and the pattern is unrecognizable. Give it 1 galactic year, and every star map ever drawn by every civilization on Earth describes a sky that exists nowhere in the universe. Orion scattered, the zodiac dissolved, the North Star long gone from its post, and dozens of other stars have taken turns holding that position and drifted away in their turn. The sky was never a ceiling. The sky is traffic, photographed once, and the photograph is already aging. Now feel what that does to the words we have been using all night. Earlier I told you Voyager flies outward toward the constellation Ophiuchus, and that a star named Gliese 445 is coming to meet it. Both statements are true tonight, and both come with an expiration date. Ophiuchus is a pattern in Earth's current sky, and once the stars that form it scatter, saying our asteroid is headed toward Ophiuchus becomes about as useful as giving directions by pointing at clouds. Gliese 445, after its close pass 40,000 years from now, keeps right on going, swinging away on its own orbit, dissolving into the general circulation of the galaxy. Every landmark this journey ever had is temporary. Every signpost is written in disappearing ink. 1 galactic year from now, the direction Voyager launched toward no longer exists in any sky anywhere, because directions in a galaxy are drawn between stars, and the stars will not hold still long enough to keep the promise. And one more thing dissolves along with the constellations. Something I find harder to say goodbye to. The neighborhood itself. The sun was born in a litter. One star among hundreds or thousands formed from the same collapsing cloud 4.5 billion years ago. And over the ages that family has been utterly scattered around the galaxy, stirred into the crowd so thoroughly that astronomers hunting for the sun's true siblings today have confirmed only a tiny handful of candidates. That is what laps of the carousel do. They shuffle the deck. The famous stars near us tonight are temporary company, passing us the way cars pass on an interstate. And a galactic year from now, the sun will be surrounded by a completely different crowd of strangers. So will Voyager, star and machine, each riding its own lane through its own shifting crowd. And the crowds are never the same crowds twice. Here, then, is the state of things. When the great clock finishes its first tick, somewhere in the Milky Way there is a star we would still recognize as the sun, completing its lap, dressed in unfamiliar constellations, keeping company with stars that were nowhere near it when the journey began. And somewhere else in the Milky Way, on its own slightly different lap, there is a small, frosted object that a patient historian could still identify as ours. Everything else from launch day, the sky it flew under, the star it was aimed past, the neighborhood it left, has been stirred away. When the galactic clock strikes 1, every map we ever drew of the heavens is already an antique, which leaves the question that decides the rest of tonight. 2 travelers, 1 carousel, separate lanes. After 1 lap, after 4, how far apart do the lanes drift? Careful with that one. It looks innocent, and it is about to break the last tool we have. I want to close this act by doing something slightly dangerous. I am going to try to break the entire premise of tonight's video. On purpose. Right in front of you. Because there is an obvious objection to everything I have said about the map dissolving. And if I were listening tonight, it would be bothering me too. The objection goes like this. You keep saying nobody can tell us where Voyager will be. But we know the laws. Gravity has been understood since Newton, refined by Einstein, tested to exquisite precision. We know the galaxy's mass. We know the orbits. And we own computers that can simulate almost anything. The machine has no engine and makes no choices. It is the most predictable object imaginable. A ball rolling across a table. So why can we not simply compute the next billion years, lap by lap, and print the answer? Why is this hard? That objection deserves a real answer. And the real answer is the deepest idea of the night. Our laws are fine. The trouble is that the galaxy plays a game where being almost exactly right is worth nothing. Watch the game in action. To predict the asteroid's path, you feed a computer its starting position and speed, and then, lap after simulated lap, the computer adds up every gravitational tug along the way. And the tugs are everywhere. Every star the object drifts past pulls on it. Nothing dramatic. No capture. No collision. Just a faint lean toward each passing star. The way you lean when a truck passes on the highway. One lean bends the path by a whisker. And a computer handles a whisker without complaint. But look at what waits down the road. The bent path arrives at the next encounter in a slightly different place than the unbent path would have, which changes how close the next star comes, which changes the size of the next lean, which changes the position after that, and the encounter after that. The errors refuse to sit quietly and add up like coins in a jar. Each error changes the future errors. Each whisker multiplies the next whisker. Scientists have a name for systems that behave this way. And you have heard it before. Chaos. And chaos in science means something sharper than disorder. It means a system where two paths that start almost identically, given enough time, end up wildly, unrecognizably apart. Here is the picture the chapter title comes from. And let me be straight about what it is. This is an illustration of sensitivity, a way to feel the principle. And nobody has run this particular experiment as a precise calculation. Take two copies of Voyager and launch them side by side, identical in every way except one. Tilt the second one's course by the width of a single human hair. On launch day, no instrument on Earth could tell the two paths apart. For 1,000 years they fly together like wingmen. For 100,000 years. Still practically touching. But every star they pass leans on them from an infinitesimally different angle. And every lean compounds. And somewhere out in the millions of years, the gap between the twins stops being microscopic and starts being real. Mille. 1,000 miles. A light year. Run the arithmetic of compounding long enough, and the twins no longer share a neighborhood. One hair's width at the starting line. Light years at the finish. And now, the trap closes. Because ask yourself how precisely we know the real Voyager's starting conditions. To within a few miles. I told you proudly in Chapter 1. And it is a genuine triumph. It is also trillions of times cruder than a hair's width. We were never the careful launcher in this story. We launched an entire swarm of possible Voyagers. Every one of them consistent with our best measurements. And given 1 billion years, the galaxy can spread that swarm across distances measured in light years, with no way, even in principle, to ask which one was real. And the passing stars are only the smallest hands in the game. The galaxy has heavier ones. Drifting through the disk are giant molecular clouds. Cold continents of gas massive enough to outweigh 1 million suns. and to pass anywhere near one of those bends an orbit by a full swerve instead of a whisker. The spiral arms themselves. Those glowing pinwheel arms in every picture of the Milky Way are slow-moving traffic jams of stars and gas. Waves of extra gravity that orbits drift into and out of, collecting a nudge at every crossing. None of this is exotic. Astronomers watch these forces sculpt the orbits of real stars all across the galaxy. And here is the proof of how deep it cuts. The Sun itself, over 20 laps, has been shoved around enough that nobody can trace it back. The same chaos that hides Voyager's future has already erased the Sun's past. And the birthplace of our own star is a question modern astronomy cannot answer. That is the size of the opponent tonight. So the honest conclusion stands in two parts. And the difference between them matters. Predicting this object's exact coordinates across 1 billion years is beyond any realistic power. Ours or anyone's. Because the forecast would demand knowledge of the galaxy's future that nothing can gather. And because every microscopic gap in that knowledge gets amplified without mercy, that door is closed for all practical purposes. Forever. But hear the second part. Because it saves the night. Chaos scrambles the details. It cannot break the leash. Shuffle the swarm of possible Voyagers, however the passing ages like, and every path in it still belongs to a bound object. Still short of escape speed by a factor of 2. Still circling the center of the Milky Way on the carousel. Chaos decides where on the track. It does not get a vote on whether the track holds. The details are lost. The shape survives. And the shape, it turns out, is enough. Enough to carry us to the year 1 billion and describe, honestly and specifically, what is there. That is Act 3. The question is no longer whether we can track this object. The question is what actually arrives at the 1 billion year mark. Stay with me. We are going to go find out. So here we are. After everything the night has thrown at us. The silence. The softening map. The hair's width and the swarm. We have finally arrived at the destination printed on the poster. 1 billion years from now. Set the great clock properly and read it out loud. 1 billion ordinary years. Divided by 1 lap of the Milky Way. Comes out a little past 4. 4 galactic years. 4 spins of the largest hand there is. The Sun has carried its whole family around the galaxy about 4 1/3 times since a rocket left Florida on a September morning. And somewhere out in that same turning disk, our asteroid has been making laps of its own. Time to ask the question with the whole night behind us. Where is it? You now know enough to see why the answer has to come in layers. Because after Chapter 12, honesty demands we sort every claim into one of 3 piles. What physics guarantees, what physics considers likely, and what nobody can know. Most stories blur those piles together. Tonight we keep them separate. And watch how much survives in each one. Start with the guarantees. The pile chaos cannot touch. Voyager 1 is in the Milky Way. Still, that is not a guess and not a probability. It is bookkeeping on a speed deficit that nothing in an empty galaxy can repay. It never crossed to another galaxy. And it is not sailing the dark between them. It is inside the same city of hundreds of billions of stars it was born in. Bound by the same gravity that binds the Sun. Circling the same center, and it is still moving. At hundreds of thousands of miles per hour. Because nothing out there has any way to stop it. If you could stand outside the galaxy in the year 1 billion and see our whole spiral spread below you like a lit city from a night flight. Somewhere in those glowing streets. That machine is there. Everything chaos scattered. It's scattered inside the city limits. Now, the second pile. the likely, and it holds more than you might expect. The machine's lap has a personality, inherited on launch day and never surrendered. It rides the disk of the galaxy roughly the way the sun does, a circuit of a couple 100 million years, and its path likely runs a little less round than the sun's, swinging somewhat closer to the galactic center at one end of the lap and somewhat farther out at the other. And remember which way Saturn threw it. Up and out of the plane of the planets. That tilt aims it through the thickness of the galactic disk. So its long-term rhythm likely includes a slow rise and fall, climbing above the crowded midplane, arcing over, sinking back through. The way a carousel horse rises and falls while going around. Picture the year 1 billion, and the likely picture is this. A frosted machine somewhere in the broad middle territories of the disk, neither down in the packed core nor out past the rim, riding a lane of its own, at some height above or below the plane that nobody can call, probably still in the same general ring of the galaxy where it was built, probably still keeping galactic time the way the sun keeps it. That is the expected story, and it would win any wager. And then the third pile, the unknowable. And now you know exactly why. It is unknowable rather than merely unknown. Which side of the galaxy is it on? No one can say. The swarm of possible Voyagers has had 4 laps to spread. And 4 laps is plenty. Where does it sit relative to the sun? The question the whole internet thinks it already answered. Take the honest range. The 2 travelers have been circling the same center on similar laps at similar speeds. And similar, compounded over 1 billion years. Can land almost anywhere. They may be on opposite sides of the disk, separated by tens of thousands of light years of stars. They may share a broad quadrant, a few thousand light years apart. And there is a strange slice of possibility in which the drifting lanes have wandered back toward each other, putting the machine closer to the sun than any headline would dare print. Nobody can rank those outcomes precisely. And after tonight, you know that is a property of the galaxy, and no failure of the astronomers. What every outcome shares is the part that matters. Every single one keeps the machine on the carousel. Every single one keeps it circling. Every single one keeps it, in the largest sense the word has ever carried, home. So here is the sentence I have been waiting all night to hand you. The most repeated line about this mission, the one in 1,000 articles, says that Voyager 1 has left home. And now you know what that line is worth. It left the house. It never left the hometown. And it never can. The odometer is vast beyond imagining, and every mile of it is curved. The straight line escape those miles were supposed to by never happened, because there are no straight lines in a galaxy. After 4 galactic years, Voyager has not left home. Home simply turned out to be the size of the Milky Way. But something is missing from this picture, and you may already feel it. All night, we have measured this journey against one landmark, the sun, the gap between 2 travelers, the star and the machine. And I have let you quietly assume that the landmark holds still in one particular way. That the sun of the year 1 billion is the sun you saw this morning. Warm and yellow and ordinary, shining on a blue world full of noise. Before we can finish this story, we have to turn around and look at that assumption. Because of the 2 travelers that parted ways in 1977, the machine is not the one the next billion years will change the most. There is one photograph from this mission that outranks all the others, and it very nearly did not exist. In February of 1990, the cameras aboard Voyager 1 had been idle for years and were scheduled to be shut down for good. The planets were done. Every picture the mission had promised was already in the archive. And camera time cost money and power. But one member of the imaging team, a scientist you have almost certainly heard of, named Carl Sagan, had spent a decade lobbying for a single last exposure with no scientific value at all. Before the cameras die, he argued, turn them around, point them backward, at us. And so, the machine, 4 billion miles from home, swung its platform one final time and took the family portrait. And in one frame, suspended in a stray shaft of scattered sunlight, there hung a single pale blue dot, less than 1 pixel wide. Earth, everyone who has ever lived, in one dusty pixel of light. Photographed by the most distant camera our species ever sent anywhere. I bring that photograph up now, at this exact point in the night, for a reason that has nothing to do with sentiment. That picture is evidence. It is the last full portrait in Voyager's family album, the final record of what home looked like while the machine still had eyes. And the question this chapter has to answer is brutally simple. In the year 1 billion, how much of what is in that pixel is still there? Take the inventory from the top, starting with the good news. The sun will be there. 1 billion years is an eternity for machines and maps. But it is comfortable middle age for a star. The sun is about 4.5 billion years old, roughly halfway through its supply of hydrogen fuel. And in the year 1 billion, it will still be exactly what it is tonight. A steady, working star, faithfully making its laps of the galaxy. The dramatic endings you may have heard about. The swelling into a red giant. The swallowing of the inner planets. All of that belongs to a much later chapter. 4 or 5 billion years further on. Far beyond the edge of tonight's story. On the night our asteroid completes its 4th galactic year, the sun still shines. The Earth, the physical planet, the ball of rock and iron, still holds its orbit. On the largest ledger, the family survives. But stars, like people, change in ways that never show up in a head count. The sun has a slow habit, and the habit decides everything in this chapter. It is getting brighter. This is the settled physics of how stars like ours age. As the sun burns hydrogen in its core, the core gradually contracts and heats, and the furnace runs a little hotter with every passing age. The pace is beyond gentle, roughly 1% brighter every 100 million years. Utterly invisible across all of human history. Tonight, though, we are working with 1 billion years. And across 1 billion years, that gentle habit adds up to a sun, something like 10% more luminous than the one that lit this morning. 10% sounds survivable. Here is why it is not. At least for the world in the photograph. The Earth's climate is a system with one deep vulnerability, and the vulnerability is water. Warm the world enough, and the oceans evaporate faster, loading the air with water vapor. Water vapor is itself a powerful greenhouse gas. So the extra vapor traps more heat, which warms the oceans further, which lifts still more vapor into the sky. Climate scientists who model the deep future all find the same cliff waiting along that road. The point where the loop stops being a thermostat and becomes a runaway. When exactly Earth reaches the cliff is genuinely uncertain, and the honest range is wide. Some models place the beginning of the end near the 1 billion year mark. Others give the oceans hundreds of millions of years beyond that. And a few stretch the timeline further still. Where the models agree is on the direction of the road. By roughly 1 billion years from now, the era of a comfortable, blue, ocean-covered Earth is either ending or already over. The seas lose ground across ages. Evaporation outrunning rain. Water climbing high into the sky, where sunlight splits it apart and the hydrogen leaks away into space. Molecule by molecule. Forever. Somewhere in the broad era, our story is set. The pale blue dot stops being blue. What remains in orbit is the same planet wearing a different face. Hot, dry, streaked with cloud under a heavier sky. Still turning. Still faithful to its star. And no longer the place in the photograph. And now you can see the true shape of the ending we have been walking toward all night. Because the roles have quietly reversed. For 50 years, every story about this mission cast Voyager as the fragile one. The doomed little machine coasting away to be lost, while the Earth stood permanent behind it. Run the clock a billion years, and the casting flips. The machine endures, frosted and patient, because interstellar space asks almost nothing of it. The living world it photographed is the one on a deadline, because the living world was always the delicate one. A thin, damp film on a rock, balanced inside a narrow band of temperature, running on borrowed stability. Bolted to the side of the machine there is a gold-plated record, and among its tracks, between the greetings and the music, there is one that is nothing but waves breaking on a shore. In the year 1 billion, it is entirely possible that the sound on that track is the only ocean Earth has left. The machine never left the galaxy. The home it left never went anywhere. Both statements are true, and together they add up to the strangest homecoming physics can write. Voyager stays in the hometown forever. The hometown just stops being anywhere it has been, somewhere in the year 1 billion. Then, a small dark object rides its lane through the Milky Way. We have spent all night establishing that it exists and sorting out where it can and cannot be. Now, I want to fly you alongside it, close enough to touch, and ask the question every museum on Earth quietly wrestles with. What is this thing now? Because there is a difference, a real one, between an object surviving and an object remaining itself. And after 4 galactic years of dust and radiation, that difference is where the truth lives. Here is a tool for questions like this one. Whenever you ask whether something old is still the thing it was, you are really asking 4 separate questions stacked like floors in a building, each one harder to reach than the one below it. Floor 1. Does it still exist? Floor 2. Could you still recognize it? Floor 3. Does it still work? Floor 4. Could you still read what it carries? An ancient Roman coin dug out of a farmer's field usually climbs all the way up. Still there. Still obviously a coin. Still doing its job of being money in the eyes of a historian. Its emperor's face still readable after 2,000 years. A sword from the same field might stall on floor 2. A blade-shaped stain of rust in the soil. Present and recognizable and nothing more. Keep the building in mind. We are going to carry Voyager up it, floor by floor, and see how high it climbs. And remember, the fine print from Chapter 10 covers this whole climb, barring that rare destructive stroke of cosmic bad luck. What follows is the expected story. Floor 1. Existence. And this floor is solid. Nothing in interstellar space is positioned to destroy this object. We ran the collision numbers back in the Oort cloud, and they only get friendlier out here, where the gap between anything and anything is measured in trillions of miles. Erosion is real and heartbreakingly slow. A frosting of surfaces. A rounding of edges. Nowhere near enough to consume a 1-ton body in the time on the clock. The object endures. Floor 1. Passed. And passed easily. Floor 2. Recognition. And the climb gets interesting. Picture what a visitor would actually see. The architecture holds. Because vacuum preserves architecture, the great dish of the main antenna, 12 feet across, still spread like a held-out palm. The long boom still reaching away from the body. The frame, the struts, the folded geometry of a thing that was assembled rather than grown. And that phrase is the whole ballgame on this floor. Nature does not build like this. 4 billion years of chemistry in this galaxy has produced comets and rocks and dust beyond counting. And not one of them has a parabolic dish, a hinged boom, or a bolt. The blankets of insulation have long since gone brittle and shredded away. The coatings are dulled. The surfaces frosted with 1 billion years of microscopic craters. And none of it matters to the verdict. The shape of intention survives. Any eye that ever finds it, in any age, would know within 1 second that somebody made this. Floor 2. Past. Though the paint did not make the trip. Floor 3. Function. And here the climb ends. Hard. Nothing works. It is easy to slide past this. So let it land properly. The computers fell silent in the 2030s, and 1 billion years of cosmic rays have since rewritten their circuits at the atomic level, turning ordered silicon into scrambled stone. The plutonium in the generators has a half-life measured in mere decades, which means it spent its usefulness inside the first few centuries and has passed the rest of the eon as a cool, inert lump. There is no scenario, none, in which some future finder presses a button and this machine hums awake. The working Voyager, the one that flew past Jupiter and photographed a pale blue dot and radioed home across 16 billion miles, existed for about 60 years out of 1 billion. A flicker at the very front of the story. Floor 3. Failed. Permanently. And through no fault of the builders. The universe simply does not carry spare parts. Which leaves floor 4. The strangest floor in the building. Does the object still carry anything readable? And here the story turns. Because the people who built this machine thought about exactly this question. And they answered it with hardware. Everything else on Voyager was designed to work for a decade or two. One component was designed for the billion-year game, on purpose, with its own armor and its own instructions. Aimed at deep time, the way the rest of the machine was aimed at Saturn. Whether that one component can still do its job in the year 1 billion is a big enough question to deserve its own chapter. So let this one close honestly. With the building half climbed, in the year 1 billion, Voyager exists. And Voyager is recognizable. And Voyager is dead. Present, unmistakable, and silent. Which forces the question every museum keeper eventually faces at exactly this point. How much of a machine has to survive before we are still allowed to call it by its name? In the summer of 1977, in the final crowded weeks before launch, technicians bolted a gold-colored aluminum case to the side of each Voyager. And inside each case, they sealed a 12-inch copper phonograph record, plated in gold. You have heard of it. The golden record may be the most famous single object our species has ever shipped anywhere. 90 minutes of music from around the world. Bach and Chuck Berry and songs older than writing. Greetings spoken in dozens of languages. The sounds of earth, wind and thunder and birds. A train, a kiss, a baby, and those waves breaking on a shore. And one track stranger than all the rest. Built from an hour in a laboratory where a young woman sat wired to sensors. A woman who had fallen in love days earlier. Her heartbeat and the electrical murmur of her brain recorded and then compressed into a brief burst of sound and pressed into the copper. A committee, led by Carl Sagan, assembled all of it in a matter of months. And etched into the record's cover, they placed a set of diagrams, instructions showing any finder how to spin the disc, where to set the stylus that ships in the case beside it, and how fast, so that the voices of Earth could play again. Tonight, the record faces our question, the billion-year question, and it deserves the same honest treatment everything else has gotten. The popular version has hardened into a slogan. The record will last 1 billion years. And the truth is better than the slogan, because the truth is a fight. 4 rounds of it. Whether the record stays with the machine, whether the grooves survive, whether the information could be pulled back out, and whether any finder could understand it. Watch each round on its own. Round 1. Staying attached. And this round is quick. The case is aluminum, bolted to the spacecraft body. And vacuum has no tools for undoing that. There is no rust to eat the bolts. No vibration to work them loose. No weather to pry at the seams. Whatever the machine is in the year 1 billion, the record is riding on it. The letter stays with the bottle. Round 2. The grooves against the sandblaster. And this is the round the designers trained for. They knew about the dust. The record was plated in gold, partly because gold shrugs off chemistry. And then, it was mounted facing inward. Its back to the machine, with the aluminum cover standing guard over the grooves. So the slow rain of interstellar grains lands on armor instead of information. Scientists who have modeled that erosion have published estimates that still stop me every time I read them. Riding shielded through the thin gas between the stars. The protected grooves could remain physically intact on billion-year timescales. And the exposed outer surfaces would need something like that long just to be visibly worn. Set that against everything else people have made. The pyramids are about 4,500 years old. And sand has already blurred their faces. The oldest cave paintings are perhaps 40,000 years old, and they survive only because caves are accidental vaults. In the year 1 billion, this gold disc stands to be one of the oldest surviving deliberate messages anywhere, made by anyone, that this galaxy is known to carry. Round 2 goes to the designers. On points. With the fine print from Chapter 10 still standing in the corner. Round 3. Recovery. And now the honest wrinkles. Grooves surviving is one thing. Playing is another. The disc was cut to spin under a stylus at 16 2/3 revolutions per minute. But no finder capable of catching a dark object between the stars would ever need to spin anything. They would image the grooves, magnify the spiral, and read the waveform straight off the metal. The way archivists on Earth already rescue music from discs too broken to touch. The deeper wrinkle is quieter. 1 billion years of cosmic rays passing through metal does not erase grooves, but it can slowly roughen a surface at the finest scales, laying a whisper of noise over the recording. A soft static of the ages settling across the voices. How much static? Nobody can certify that. For the same reason, nobody can certify any material across a span 1,000,000 times longer than recorded history. The truthful call is that the message was engineered to win this round, that the physics leans its way, and that 1 billion years always gets a vote. Round 3. Probably, with scars. And round 4. Understanding. Here the engineering ends and the gamble begins. Because no armor can protect a message from the mind of its reader. The instructions on the cover are drawn in what the makers hoped was the one universal language. Physics itself. The timing marks are keyed to the natural rhythm of the hydrogen atom. the most common atom in existence. The cover even carries a map, marking the sun's position against the beacons of 14 pulsars. Spinning dead stars that tick like lighthouses. It is brilliant. And you already know what tonight does to part of it. That map gives the address of the sun as it was, drawn in a galaxy where, as you have seen all night, everything moves. Pulsars drift on their own orbits. Their ticking slows across the ages at rates a clever finder could unwind. And still, with every galactic year that passes, the map on the cover becomes less a set of directions and more a postmark, a note that no longer says here is the sender. Only here is where the sender once was, in an arrangement of stars that no longer exists anywhere. The makers understood this perfectly. They built it anyway. And they said, why at the time? Plainly, the record was a gift thrown forward into deep time, sent for the sending. Because composing it said something about the senders that no failure of delivery could ever unsay. So tally the fight. Attached. Almost certainly. Intact. By design. With an endurance no other human object is even built to attempt. Recoverable. Probably. Under a soft static of ages. Understood. Unknowable. And step back one step. Because the strangest part of this chapter is who the record turns out to be for. In the year 1 billion, as we saw, the world it describes may no longer exist on Earth. The waves on track after track of ocean sound may have outlived the oceans. The heartbeat in the copper may have outlived the species that felt it. The message was built to outlive the sender. And it will. Nobody promised it a receiver. One question is still hanging over this whole journey. And you have been patient about it. So let us face it squarely before we write the final coordinate. The record endures. The machine endures. Fine. Does anyone ever actually find it? A message that lasts 1 billion years is remarkable. A message that lasts 1 billion years and gets read is a miracle. Which one is this? This is the exact spot where stories about Voyager usually leave the road and drive off into pure fantasy. So, let me set the rules for this chapter up front. No invented aliens tonight. And no invented odds either. What I can give you instead is the honest geometry of the problem. And the geometry is so lopsided that it answers the question all by itself. Start with what the object gives a searcher to work with. And the answer is almost a perfect nothing. It makes no light of its own. The radio has been cold since the 2030s. It reflects only whatever faint starlight happens to fall on it. And out between the stars, that is barely anything at all. It is one of the darkest, quietest, smallest things in the entire galaxy. A needle that stopped shining before it even properly left the haystack. Astronomers on Earth today can find asteroids the size of a house at distances of millions of miles. And it takes our best instruments to do it. Whew, with the sun helpfully lighting the target. Now, shrink the target to the size of a car. Turn off the lighting. And move the search out to the space between the stars. No telescope in existence, and none on any drawing board, could detect Voyager at even a fraction of a light year. Sit with what that means about us. Our own species. The one that knows exactly what it built and roughly where it sent it. Lost the ability to see this object the moment it left the neighborhood. If the radio went quiet, unannounced tomorrow, we could point every instrument on Earth at the sky and never find our own machine again. Now widen the frame to the searcher we cannot name. Suppose, and it is only a suppose, that somewhere in the Milky Way, across the next billion years, there are other eyes, other instruments, other curiosities. Look at what finding this thing would actually require. Existing at the right time. Somewhere inside the eon, the object spends drifting, being in the right place, in a galaxy 100,000 light-years across. Near the one thin thread, the object traces through it, owning instruments sensitive beyond anything we can currently imagine, capable of picking a dark speck of metal out of the black at meaningful range. And even then, unless the object happened to wander through their own home system, they would need a reason to look at that exact patch of nothing at that exact moment. Every condition on that list is demanding. All of them together. Stacked. Make the word unlikely feel generous. I promise no fake numbers. So, I will not dress this up as a percentage. The plain version is enough. The default fate of this object, the overwhelming, ordinary, expected fate, is to drift forever and never be seen by anyone or anything at all. Before that lands as sad. Though, look at the two facts that change its temperature. The first is that every search is a lottery. And this ticket never expires. A civilization gets its window of centuries, and then history moves on. Voyager's window is the eon itself. It crosses the galaxy's lanes again and again. 4 laps per billion years and counting. And if the Milky Way ever does fill with watchers, in this age or any age after, the needle is still in the haystack, still carrying its 90 minutes of Earth. Terrible odds per year. Strangely alive across all of time. No message our species ever sent has had odds shaped like that. The second fact is stranger, and it settles the chapter. Being found was never the assignment. The people who made the record knew this geometry. In 1977, Sagan himself said plainly that the record would probably never be intercepted, and that the launching of this bottle into the cosmic ocean mattered anyway, because of what it said about the people doing the launching. 2 machines leaving forever. And their builders spent the weight allowance on Bach and birdsong and a heartbeat. That choice finished its real work here, on this planet. The day it was made. Everything after is bonus. So, here is the honest bottom line. Voyager is not hiding. It is simply smaller than the odds of ever being seen. And that turns out to be fine. Because this particular needle was never really thrown for the finding. It was thrown for the throwing, which clears the desk at last. No suspense left. No questions parked at the roadside. All that remains is the thing we came here to do. It is time to write the address. Come back to Pasadena with me one last time. The quiet room. The screen. The row of numbers we met at the start of the night. Right now, tonight, those numbers are a fact. A living spacecraft answers them. A dish in the California desert confirms them. And on November 18th, 2026, in the small hours of the morning, at a moment already calculated down to the second, they will read 1 light day exactly. I told you then that this precision was a candle, and that tonight was the story of how it goes out. So let us watch the whole arc of it. One final pass, and see the number change shape as it falls through time. Tonight, the position of Voyager 1 is a number. A dot on a screen, 16 billion miles out. Sharp as a pin. In the 2030s, the radio dies, and the number becomes a prediction. The screen looks the same. The dot still moves, but nobody can ever check it again. And a fact you can never check again has changed species. At 40,000 years, as a dim red star slides past in the dark, the prediction becomes a path, a short, bright line of possible positions, still narrow, still proud of itself, threading off the sun's emptied property toward open country. At 1 million years. Out at the edge of the best map our species ever drew. The path becomes a corridor, a widening cone of maybe headlight beams opening into fog. The object certainly inside, and certainly nowhere in particular. And at 1 billion years, the corridor gives way to the only honest coordinate left. Here it is, assembled from everything this night has proven. Sorted exactly the way Chapter 13 taught us to sort it. The guaranteed first, the likely second, the unknowable last. 1 billion years from now, Voyager 1 is in the Milky Way galaxy. It never had the speed to leave. And speed is a thing you cannot find lying around in empty space. It rides a bound orbit around the galactic center. One lap every couple 100 million years. Tilted against the disk. Rising above the plane and sinking back through it like a slow carousel horse. 4 laps are behind it. More or less. And its true odometer is staggering. On the order of 700,000 light-years of actual road. 13 times the number in all the headlines. Every mile of it real, and every mile of it curved. Most likely, it still rides the broad middle territories of the disk. The same general ring of the galaxy where it was built, on a lane of its own. And where it sits along that lane? Which side of the galaxy? What height above the plane? How many light-years from the sun? Those details belong to chaos now. Spread across a swarm of possibilities that no mind and no instrument will ever collapse back into a dot. Because the galaxy does not keep the records that answer would require. The best address anyone will ever write for it is the true one. Somewhere in the Milky Way, still moving. And say the rest. Because the rest is what makes the address worth writing. Barring that one rare stroke of cosmic bad luck, the thing at that address is still recognizable at a glance. Frosted by 1 billion years of dust. Scarred by radiation. Dark and cold and silent. The shape of intention still hanging on its frame. A working machine for 60 years. A monument for the rest. Bolted to its side rides one of the oldest surviving deliberate messages this galaxy is known to carry. A gold disk of greetings and thunder, and Bach. A compressed heartbeat, and the sound of waves breaking on a shore that, by then, may be the only ocean Earth has left. Its home star still shines. Its home world still orbits. And the blue in its most famous photograph may survive nowhere at all, except as a pattern in the grooves it carries, and in whatever the finders of deep time never come to find. One more thing before we say goodnight, and it is the reason I built this whole evening the way I did. Think about what November 18th, 2026 really is. For one moment, early that morning, an entire civilization will know the position of this object to the second and to the mile. And we will celebrate, and we should, but you now know what that moment is in the long story. It is the peak, the high watermark of knowing, from that morning forward, for the rest of time. The answer to the question, where is Voyager 1, only ever gets blurrier. Every year of silence spreads the swarm a little wider. Nobody who comes after us will ever know its position as well as we know it right now. Most questions about the future sharpen as their moment approaches. This one is finished sharpening in our lifetime. And will spend 1 billion years going soft. You are living inside the last era. Ever. In which anyone can point at the sky and say, with certainty, it is there. So the next time you are outside on a clear night, you do not need to find any particular star. Every part of that sky is the same address now, somewhere behind it. A small frosted machine from 1977 is making its long left turn around the galaxy, carrying a heartbeat and the sound of the sea, keeping the only appointment it has left, the slow lap, the rise and fall through the plane of the Milky Way, around and around, on the house, forever. If this journey changed the way you see that machine, or that sky, a like and a subscribe genuinely help this channel keep making nights like this one. But that can wait until morning. For now, turn off the screen, close your eyes, and picture the dot on the map in Pasadena. Still confirmed. Still a fact. For a little while longer, good night to you, and good night to the smallest asteroid in the Milky Way.